In this class, we will first try to represent the angular momentum operators in spherical polar coordinates, and then we will try to get the eigenvalues and eigenfunctions of orbital angular momentum. Now, in order to determine the eigenvalues of orbital angular momentum, it is convenient to express the operators in spherical polar coordinates. For orbital angular momentum, we use the operator L specifically because we have seen in previous class in general case we were using the operator J to represent the general angular momentum, but here we will be using L. So the components of this orbital angular momentum are Lx, Ly and Lz. Now in spherical polar coordinates, these components are given by Lx is given by Lx is equal to IH cross sine phi dou by dou theta plus cot theta cos phi dou by dou phi, and Ly is given by IH cross minus cos phi dou by dou theta plus cot theta sin phi dou by dou phi, and Lz is given by Lz equal to minus IH cross dou by dou phi. So if you put all these things together, we can define the L square operator similar to our J square operator. L square is given by minus H cross square 1 by sin theta dou by dou theta sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square. So if you want to know how to get these operators in spherical polar coordinates, the complete derivation is given in the textbook by Quantum Mechanics by Ajay Ghatak, or you can refer the textbooks by Noordin Setli, where you can see how to get these things in spherical polar coordinates. Okay. Now usually for the derivation of the eigenvalues or the eigenfunctions of the orbital angular momentum, we use two operators, two ladder operators similar to our J plus and J minus. We use L plus and L minus. So L plus is defined in a way similar to our J plus. So the L plus operator or the raising operator is defined as Lx plus I Ly, and L minus is defined as Lx minus I Ly. So this is these are the things we need to start our eigenvalue problem for the orbital angular momentum operator. So let's see how to get the eigenvalues and eigenfunctions of orbital angular momentum. If you carefully analyze the expression for Lz and L square, you can see that here in the expression for Lz and L square expressions, it depends only on the angles theta and phi. and their eigenstates, therefore we expect it depends only on theta and phi, and we denote this common eigenstate as y theta phi, common eigenstates of Lz and L square, because we expect that the eigenfunction should depend only on theta and phi, because there is no r dependent terms in the expressions for Lz or L square. So we can write the eigenvalue equations for L square operator as L square y theta phi is equal to lambda h cross square y theta phi. So if we substitute for L square from the spherical polar coordinate representation we have seen just before, we can write it as this expression can be written as minus h cross square into 1 by sine theta dou by dou theta sine theta into dou by dou theta plus 1 by sine square theta dou square phi dou square by dou phi square. Then you have y theta phi is equal to lambda h cross square y theta phi. That means we can write it as 1 by sine theta dou by dou theta sine theta dou by dou theta into y theta phi plus 1 by sine square theta dou square y by dou phi square plus lambda y theta phi is equal to 0. So where we have assumed that these y theta phi are continuous functions of theta and phi. Now we use the method of separation of variables, the standard technique that we have used several times in quantum mechanics. So with that we split this y theta phi as the product of two independent functions, theta of theta and phi of phi, where this capital theta depends only the variable small theta, and the capital phi depends only the variable small phi. So if you make this substitution here, you can write this expression as 1 by sine theta dou by dou theta sine theta dou by dou theta of capital theta capital phi plus 1 by sine square theta dou square by dou phi square of capital theta capital phi plus lambda capital theta capital phi is equal to 0. So if you rearrange this expression, we can write it as capital phi by sine theta. Now the partial derivative can be written as a completed derivative d by d theta into sine theta d by d theta into capital theta plus capital theta by sine square theta d square capital phi by d phi square plus lambda capital theta capital phi is equal to 0. Now if you multiply these entire expressions by sine square theta, and if you divide it by capital theta and capital phi, then and if you separate the terms involving capital theta at one side and capital phi at the other side, you expression like this: sine square theta by capital theta into 1 by sine theta d by d theta sine theta d by d theta plus lambda into theta is equal to minus 1 by capital phi d square phi by d phi square. So these exercise we have done several times using the method of separation of variables. Now you see that the left hand side is a function of capital theta and right hand side is a function of capital phi. And we know that this is true only if the both sides are separately equal to some constant, and we take that constant as m square because both sides are separate variable dependence. Okay, so now from this equation let's try to get the solution or the eigenfunctions of Lz. So for that we first consider this part. We consider the right hand side of the expression that will give us d square phi by d phi square plus m square phi is equal to 0. So what we are trying to do is we are trying to get the eigenfunction of Lz operator. Now the solution to this problem we have done to this expression we have done several times, and I'm not repeating the same thing, so you know that the solution for this simple second order differential equation is given by capital phi is equal to some constant into e raised to im phi. And if you impose the condition that the wave function must be single valued when this angle theta is changed by theta plus 2 pi, then we get some restriction on the values of this variable m, and we have seen that this is possible. M can be only have values like 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. We have done similar problem in the previous semester. Okay, and then this value for a can be obtained by normalizing the wave function. So if you do all these things, you will get the eigenfunction for Lz as phi m of phi is equal to 1 by root 2 pi e raised to im phi with the values of m given by these kind of things. So this is the eigenfunction of Lz operator, and we label it with this subscript m because it depends on the values of m. Now the orthonormality condition is given by integral 0 to 2 pi from the general property of the spherical polar coordinates. You can write it as phi m prime of phi phi m of phi d phi is equal to delta m prime. Yeah. And now we take this part, the left hand side, along with this constant m square. So that will lead us to an expression of the form sine square theta by capital theta into 1 by sine theta d by d theta sine theta d capital theta by d theta plus lambda capital theta is equal to m square, or we can write it as 1 by sine theta d by d theta sine theta d capital theta by d theta plus lambda minus m square by sine square theta into capital theta is equal to 0 by simply rearranging the terms. Now if you make some substitutions like cos theta equal to x and capital theta is equal to f of x, then this expression can be written as, you can verify it yourself. You can verify that you will get expressions like this one, the above expression. This one will become, if you make the substitution, this will become minus d by dx sine theta into minus sine theta d by dx into f of x plus lambda minus m square by 1 minus x square into f of x is equal to 0. Or you can write it as d by dx into 1 minus x square d by dx into f of x plus lambda minus m square by 1 minus x square into f of x is equal to 0. Now we consider two separate conditions. In the first case, we take m is equal to 0, right? So if m is equal to 0, this expression will be can be written as 1 minus x square d square f of x by dx square minus 2x into d f of x by dx plus lambda into f of x is equal to 0. You can see that this is the similar to the Legendre's differential equation, right? The Legendre's differential equation. So here you can try the power series solution for f of x, and now the convergence of this power series solution demands that lambda must be equal to L into L plus 1, where this L can have values 0, 1, 2, 3, etc. Right? So the eigenvalue equation can be written as, for the L square operator, we can write it as L square y, which was considered as functions of small theta and phi. Now we put two subscripts L and M because it depends on these two numbers L and M. So this is equal to, in place of lambda we write L into L plus 1 H cross square Y Lm theta phi. So the eigenvalue equation becomes like this, with the eigenvalue given by L into L plus 1 H cross square. Okay. Now if we go back to this expression 1 by sin theta, this expression, and if you put the value for lambda, we will get an expression 1 by sin theta d by d theta sin theta d by d theta of capital theta plus, now in place of lambda we put L into L plus 1 minus m square by sin square theta into capital theta is equal to 0. Now this is known as the Legendre differential equation, and its solution can be expressed in terms of associated Legendre function. Associated Legendre function PLM cos theta. We have seen this associated Legendre function in previous semester also. So the solution for this expression is given by the associated Legendre function. So we can write the solution for capital theta, which is a function of small theta, and now you can write theta which depends on these two numbers L and M. So we can write it as theta Lm. So this is given by some constants CLM PLM cos theta, the associated Legendre function. Now the value of constant CLM can be determined from the orthonormalization condition, and if we do that from the orthonormalization condition of this associated Legendre polynomial, we will get this value of CLM as given by minus 1 all raised to m square root of 2l plus 1 by 2 l minus m factorial divided by l plus m factorial for m greater than or equal to 0. So if you substitute this thing back into this expression for theta Lm, we can write the solution for the orbital angular momentum capital theta Lm of small theta is equal to minus 1 all raised to m square root of 2l plus 1 by 2 l minus m factorial by l plus m factorial PLM cos theta. So this is the solution to the theta part. So if we join the eigenfunctions of L square and Lz, then we will get the eigenfunction YLM theta phi for L square operator. This is given by minus 1 all raised to m square root of 2l plus 1 by 2 into l minus m factorial divided by l plus m factorial PLM cos theta. Then we have e raised to im phi. So these are called the normalized spherical harmonics. Normalized spherical harmonics. So the eigenfunctions of orbital angular momentum are given by the spherical harmonics. Okay. Now we have seen it for one particular case for m is equal to 0. Now if we want to consider the case for m not equal to 0, in that case we have to make use of the operators, the L plus operator or L minus operator. So the typical procedure is we start from the value, suppose we have a state of L and m equal to 0, L0 state. Now if you act on this with this raising operator, we can reach the state L1, that is m is equal to 1 state. And if you once again act this L plus operator on this one, then that will give us small l state 2, like that. So higher states can be determined starting from this value of m is equal to 0 to higher values can be determined by the action of the L plus operator. Okay, or you can go below these values, you can act L minus operator, that will give us states like L minus 1, L minus 2, etc. So that is the typical procedure we use to get the eigenfunctions or the states for other values of m.
However, we cannot indefinitely raise the states by the continuous operation of L plus operator, or we cannot indefinitely go to states lower than m is equal to 0 by the continuous action of L minus operator. So the maximum value that the m can take is limited by the values of L. So m can vary from plus L to minus L or minus L to plus L, including the 0 state. So m can have only the integer values within this limit plus L to minus L. So the values of m are ultimately limited as m can have values from minus L plus 1, etc., 0, etc., L minus 1 up to plus L. So there can be 2 L plus 1 values in general. Okay, so what we have seen is that we have seen two quantum numbers in the orbital angular momentum case. The quantum number L, which can have integer values from 0, 1, 2, 3, etc., and its projection, or it is called the magnetic quantum number m. This is sometimes represented with a subscript L because we will be having another projection with the spin angular momentum. So to identify or to distinguish it, we sometimes represent the magnetic quantum number m associated with the L as ml, and this ml can have values from minus L to plus L. So there are two L plus 1 values. Okay.